ANCOVA is the analysis of differences between means in more than two groups when there's also a covariate involved. A covariate is a continuous variable that is not part of the main experimental manipulation, but has an influence or explains variance on the outcome or dependent variable. A covariate could be included to reduce within-group error variance by explaining some of the unexplained variance in terms of covariance, which allows us to more accurately assess the effect of the independent variable. Covariates can also serve to eliminate confounding variables by allowing them to be identified and entered into the analysis as a covariate, which eliminates its influence on the dependent variable being measured. You must make sure that the covariate only shares its variance with the unexplained variance and not with the experimental effect before conducting an ANCOVA. You must also check for the assumption of homogeneity of regression slopes to make sure that the overall relationship between the covariate and outcome variable is true for all groups of participants. You follow up by computing contrast or post hoc tests depending upon if you have a hypothesis or not. Order matters in the ANCOVA, so you must choose which type of squares to include. You interpret the covariate in the ANCOVA by looking at the b-value. If the b-value for the covariate is positive, then it means that the covariate and the outcome variable have a positive relationship. If the b-value is negative, it means that the covariate and the outcome variable have a negative relationship. You are able to report effect sizes in ANCOVA models. My research design has three groups with understanding scores of 1 to 6 about reversal theory. Group 1 had no training, Group 2 was given a book to read about reversal theory, and Group 3 was given the book and a lecture about reversal theory. The covariate was IQ scores. Group 2 and 3 will have higher knowledge about reversal theory than Group 1, but Group 3 will have higher understanding scores than both Group 1 and 2. Knowledge scores is the dependent variable, the groups are the independent variables, and IQ scores is the covariate. I conducted an ANCOVA because I'm computing the means between three groups and a covariate is present. I had a categorical predictor variable with three levels, a continuous outcome variable, and a continuous covariate variable. This is my data set. There are 170 participants with knowledge scores between 1 and 6 and IQ scores between 90 and 30. I installed the packages necessary to run an ANCOVA. The package car is used for a Levene's test and type 3 sum of squares. The package compute.es is used for effect sizes. The package effects is used for adjusted means. The package ggplot2 is used to create graphs. The package multicomp is used for post hoc test. The package pastex is used for descriptive statistics. The package wrs is used for a robust test. So this is where I installed them, and this is where I libraried them. This is where I attached my data set. I converted the numeric variable group into a categorical factor by changing the numbers to their categorical titles of no training, book training, and book training and lecture. I then got the descriptive statistics for each group. This shows you the mean, the median, standard deviation, all that good stuff. I conducted a Levene's test to see whether the variance in reversal theory understanding varies across groups that receive different levels of training. The output shows that the Levene's test is very non-significant with p equals 0.27 and f equals 1.3. This means that the variances are very similar for this data. If the test had been significant, I would instead conduct a robust version of ANCOVA. I ran an ANCOVA to make sure that the covariate in the analysis is independent of the experimental manipulation. I checked to see if the covariate is roughly equal across all levels of my independent variable. I tested this by running an ANCOVA with IQ scores as the outcome and groups as the predictor. The results show that the main effect of categories is not significant with p equals 0.97, p equals 0.38, so the average of IQ scores is roughly the same across all three training category groups. This means that it is appropriate to use IQ scores as a covariate in the analysis. I then plotted it to see the graphs. The residuals versus fitted graph is used for testing homogeneity of variance. The plot shows points that are similarly spread for the three groups, implying that the variances are similar across groups. We also reached this conclusion by running the Levene's test earlier. The normal QQ plot tells us about the normality of residuals in the model. The residuals seem to be normally distributed because for the most part the dots on the graph cling to the diagonal line. If normality of errors could not be assumed, I would conduct a robust version of ANCOVA. I created a model and ran it using an ANCOVA that contains information about how well the groups or categories predict understanding about the reversal theory. I will conduct play and contrast as opposed to post hoc tests because I have a specific hypothesis that I'm trying to test. Play and contrast have 3 typical rules. If a control group exists, we want to compare it against the other experimental groups. So in my hypothesis, I want to compare the group with no training compared to the group 2, which was given a book to read, and group 3, which was given a book to read and a lecture. This rule exists because once a slice of variance has been split from a larger chunk, it can't be attached to any other pieces of variance. It can only be further subdivided into chunks of variance. Each contrast can only compare 2 chunks of variation, so in my first contrast, group 1 with no training will be compared against group 2 and 3, and in my second contrast, group 2 and 3 will be compared against each other. This rule exists so that the researcher can draw firm conclusions about what the contrast tells us. By comparing only 2 chunks of variance, we can be sure that a significant result represents a difference between these 2 portions of experimental variation. Also, another rule is that once a group has been singled out in a contrast, it can't be used in another contrast. Before I conduct the play and contrast, I must assign weights to the dummy variables. Groups coded with positive weights will be compared against groups coded with negative weights, and the sum of weights for a comparison should equal 0. If a group is not involved in the comparison, it automatically is assigned a weight of 0, which eliminates that group from all calculations. For a given contrast, the weights assigned to the group or groups in one chunk of variation should be equal to the number of groups in the opposite chunk of variation. So, I must assign the weight to the first comparison. In the first comparison, I am comparing chunk 1, which consists of the experimental group, or group 2 and 3, against chunk 2, which consists of the placebo group, or group 1. One chunk must be assigned positive weights and the other assigned negative weights, so chunk 1 was assigned positive weights while chunk 2 is assigned a negative weight. The groups in chunk 1 must equal the number of groups in chunk 2, and there's only one group in chunk 2, so I assign each group in chunk 1 a weight of positive 1. The placebo group in chunk 2 receives a weight of 2 because there are 2 groups in chunk 1. So to bring it back together, chunk 1 has a weight of plus 1 assigned to group 2 and a weight of plus 1 assigned to group 3, while chunk 2 has a weight of negative 2 assigned to group 1. The second contrast group compares the 2 experimental groups, or group 2 and 3, and ignores group 1. So we give group 1 a weight of 0, which eliminates it from calculations. I will assign chunk 1, which is group 2, with a weight of negative 1, and chunk 2, which consists of group 3, with a weight of positive 1. And this step binds them together. I choose to use a type 3 sum of squares because I am testing an unbalanced design. All effects are evaluated taking into consideration all other effects in the model, not just effects that were entered before. I would have chosen a type 1 sum of squares if I wanted a hierarchical regression, in which I put one predictor in the model and then another, and the second predictor would be evaluated after the first predictor. I would have chosen a type 2 sum of squares if I wanted all of the effects to be evaluated taking into consideration all other effects in the model, except for higher order effects that include the effect being evaluated. Type 2 and type 3 sum of squares are the same as far as the highest order term is concerned, and type 4 sum of squares are essentially the same as type 3, but they are designed to be used when there's missing data. I have to adjust the means for the effect of the covariate. The object created gives us the information about the effect of the different groups. When the means are adjusted for the effect of the covariate, the means across the 3 groups stay relatively the same. No training has a mean of 4.69, book training has a mean of 4.52, and book training and lecture has a mean of 4.66. The standard errors for each group are 0.13 for no training, 0.16 for book training, and 0.18 for book and lecture. My ANCOVA reports that there is no significance between the no training group and the combination of the book training group and book training and lecture group. In contrast, 1, p equals 6.619. There's also no significance found in contrast 2, which compares the book training group to the book training and lecture group, and p equals 0.826. I created a scatter plot to confirm what I already know about my data models and the relationships between the covariate and the dependent variable. I tested the assumption of homogeneity of regression slopes by including the interaction between the covariate of IQ score and predictor variable groups in an ANCOVA design. The p-value equals 0.27 of the covariate by outcome interaction, so the assumption of homogeneity of regression slopes has not been broken. This is how the book tells us to get the effect sizes, but the necessary package is not available for the new R versions. So I had to create a new variable to be able to run the effects on each individual groups together. I ran this instead to see the effect sizes for the difference between the no training group and the book training group, which has a small effect of D equals 0.015 and R equals 0.07. This was run to see the effect sizes for the difference between the no training group and book and lecture training group, which has a small effect of D equals 0.03 and R equals 0.01. And this was run to see the effect sizes for the difference between the book training group and the book and lecture training group, which was also small, D equals negative 0.12 and R equals negative 0.06. It was not necessary to run the post hoc test, but I ran it regardless. The difference between the adjusted group mean for book training and no training is 0.102, for book training and lecture and no training is negative 0.049, and for book training and lecture and book training is negative 0.152. The output suggests no significance between any groups. Book training and no training have a p-value of 0.872, book training and lecture and just book training have a p-value of 0.973, and for book training and lecture and just book training, p equals 0.8.